It's a lovely day here in Maine. The sun is shining. It's a warm 56 degrees Fahrenheit, and it's February 1st. That may sound like a promotional statement for everyone to come and visit Maine and come move here. But a skeptical person, an empirically minded person, might ask a few critical questions. Just how typical is a 56 degree, sunny, warm day on February 1st in Maine? To find out, we would treat temperature as a variable, something we can measure about how warm or cold the air is, a characteristic that varies in its value. In order to describe that variable, we can think about two measurements: mean, what we consider the classical average value of a variable, and standard deviation. Standard deviation tells us how much away from that mean that temperature tends to vary. If you have the mean of a variable and you have the standard deviation of a variable across a number of observations, say the temperature of Maine on February 1st, you can have a much more accurate picture of what's typical, and therefore you have a much better basis for making a decision. In considering analyses, we can think about means, standard deviations, and also a statistic called D. To think about this, let's take a look at actual temperature records for Augusta, Maine for February 1st for the last 10 years from the recording of this video in 2016. As you can see from this scatter plot in which the y-axis is temperature, x-axis is year, 2016 is an outlier. How much of an outlier? We can compare it to the overall mean, which is, as you can see from the numbers on the left, 28.5 degrees Fahrenheit. It's represented by that blue line in the graph. So that's a significant difference from 2016. How much variation is there across all the years? We could look at the deviation from the mean for each year by drawing a green line connecting each of the observations, the red dots, to that overall mean. The deviation is greatest in 2016, and it's smallest in 2007 and 2008. Well, to figure out the standard deviation, we would take the deviation for each year from the mean, and then we would square it, and then add up all those squared terms, and take the average. Why do we square? Because positive deviations and negative deviations would otherwise cancel themselves out, and we want to add up the magnitude rather than having them cancel each other out. When we take the average squared deviation, then we're all of a sudden in units, not of the original measurement, so to correct for that, we'll take a square root. Now, what does distribution look like overall? What is the tendency overall for February 1st temperatures based on 10 years of data? Well, if we had every other year following the trend of these past 10 years, would look like this green curve you see on the right, in which most of the time in this normally distributed curve you have temperatures below freezing, occasionally above freezing, and very, very occasionally as warm as 56, but very rarely. Let's add a little bit of complexity to this discussion by considering that perhaps that overall trend has another sub-trend underneath. What if even years and odd years, for some reason, might have different temperature trends? As you can see in this data here, if we separate out even years and odd years, we get different means and standard deviations. A higher mean for the even years in Augusta, Maine on February 1st, and a lower mean by 12 degree points, 12.6 degree points for the odd years. There is greater variation in the even years and less variation measured by the standard deviation in odd years. And you can see what that looks like in this graph. How different are these two sets of years, the even and odd years, from one another? To figure that out, we would calculate a statistic called D. And D is nothing more than the difference in means between the two sets of years, which is 12.6 degrees, divided by the average standard deviation. And the average standard deviation here is 9.8. So we would receive a D score of 1.29. Now, in general, when you're looking at D sizes, a D size of 1.29 would be considered very large, whereas a close to 0 D score would have to be less than 0.1. 1.29 is a very large difference. And yet notice that even for this very large difference between the two sets of years, there's a significant overlap. There will be many years in the even and odd side, if these years are representative, where temperatures will be similar. A fair portion of the time, there will be no difference at all between even years and odd years. Something to notice in the last instance in this data is that differences between even and odd years, or between any two sets of groups, are likely to emerge when you have a small number of observations. In this case, we've only taken a look at 10 years worth of data. Do you think that the difference between even and odd years in temperature in Maine on February 1st would remain if we looked not at 10 years, but 100 years worth of data? Probably not. And this is why large studies of differences between groups, whether they are groups of years or groups of people, are advisable.